Okay, so intramolecular forces, those are the ones that are within the molecule. Those are going to be what our bonds are. Okay, so intramolecular forces are those bonds. Whereas when we talk about intermolecular forces, these are going to be our electrostatic forces. You may hear them called van der Waals forces. These that occur between the molecules. So these are what's holding those molecules together. So the very easy one is London dispersion forces. These are ones that occur in our nonpolar molecules. And then we have our dipole forces, and we can further classify a dipole force as hydrogen bonding. And these are going to occur in polar molecules. And hydrogen bonding is special because it only occurs between hydrogen and what atoms? Oxygen. What else? Those are double bonds, triple bonds. No, that's double triple bonds. No. It is H and N, O, or F. So HNOF. Those are the only ones that will have hydrogen bonding. If you have hydrogen there with something else, then it is a dipole-dipole force. And then you need to know that the intramolecular forces, or bonds, are stronger than IMF. So IMF is just what's holding those molecules together, whereas intramolecular, that is what's holding the elements together to make that bond. So if we're going to look here, this is just an example. Here we have hydrogen bonding. And we know that we have our dipole moment is going towards the oxygen. And if you look at this whole molecule, or what this whole thing together, all these hydrogens and oxygens, these water molecules, you can see that between the hydrogen and the oxygen, that is our intramolecular bond, whereas when you have these dots here, that is our hydrogen bond, or our IMF. And the way these line up, you see how they are lined up so that those dipole moments are situated so that the positive end of one is touching the negative end of the other, and that is why we have all those big spaces in there, and that's what makes solid water less dense than liquid water, because of all that space that's in between here, and that causes that less denseness in the water. Ice, sorry. Okay, so phase changes is when a substance changes from a solid to a liquid to a gas. The molecules remain intact. So when we change a state, what happens is the forces among the molecules are being they're being overcome. So when we boil something, or when something goes from solid to liquid, we do not break bonds. You will get a question like that on the AP exam, and you will say that, why Why? What happens during a phase change? And you'll say that the bonds are breaking. Bonds are not breaking within the molecule. What is breaking are the intermolecular forces. We are overcoming intermolecular forces that are holding the phase together. So when we go from solid to liquid, and then liquid to gas, we are breaking those forces within that molecule. We don't go from having water, liquid water, to having gaseous hydrogens and gaseous oxygens. We do not break those bonds. It is still water when we go through a phase change. Yes?
So when it goes down, like from gas to liquid, does that mean the molecular forces are getting stronger?
Yes.
Okay.
Yes.
So does that mean that there's times when it's neither liquid or gas, like it's in between?
Yes, we're going to talk about that in a minute. Okay. So do not say that you're breaking bonds when you're going through a phase change. You do not break bonds when you go through a phase change. And it says there in big letters that only IMFs are overcome. So we overcome our IMFs. So we're going to look here at a heating curve. So you should have saw this back in pre-AP. So this is a heating curve. What is happening at the slopes? Anybody remember? We get a phase. So this is a change in temperature, and these are our phases. The flat line is our actual phase change. Now, why is the ice and water phase change smaller than the water and steam phase change?
Because they're not
Specific heat of ice. What else?
the change between the distance of molecules is less.
Okay, the change distance between the molecules is less. So the IMFs are easier to overcome in a solid, from a solid to a liquid, whereas when you're going from a liquid to a gas, you have to have more energy to overcome those forces holding those molecules together. So when you have looking at this phase change diagram, and you're looking at how much heat is involved, Q equals MCAT, that is going to be our slanted lines. That is where we have our phases. Solid, liquid, or gas. Whereas if you're looking at heat of fusion or heat of vaporization, that is going to be those flat lines. And you have to calculate those numbers. So if I were to go from minus 20 in ice, and I were to take it up to liquid water at 60 degrees Celsius, I have to do 3 calculations. Okay, so I have to do a calculation for the heat of fusion. No, scratch that. Calculation for Q equals MCAT for the ice, and then I need to do it for the fusion, and then I need to do it for the water. So you need to do 3 of them, and you have to add them all together. Okay, and you have to look at your different states of matter and the specific heat for those states of matter. And we're going to look at that, do a couple of those. Questions? So this is not something you'll be tested big on, but this is just prior knowledge that you should know.
The Q equals MH, that's for for the same substance, correct?
Right. So you would have your heat of fusion of, for whatever, and the heat of vaporization.
Oh. Never mind. But
Okay. So take a look at this equation here, or this problem. How much heat energy is required to raise the temperature of 44 grams of lead from room temperature to its melting point? The specific heat of lead is 0.13 joules per gram degree Celsius. So if I'm looking at a heating curve, room temperature is, what is lead at room temperature? Solid. Okay? And we are taking it from a solid just down to its melting point. So that's the only thing I care about on that heating curve. So what equation do we need to use to solve this? Do we need to do just one equation, or do we need to do several? Just one, okay? So we just need Q equals MCAT. Our mass is 44. Our C is 0.13. And our delta T is, our final is 327 minus 21. No. So then to 2 decimal places, get that for me. Y'all have 1800? 1800 joules. Okay, hold on. I'm going to pause this real quick. So does that make sense? We are going from a solid to a liquid. So should our Q be positive, or should it be negative? We're adding heat, right? So it should be positive. So that makes sense. Now it says calculate the energy that must be removed from 25 grams of water at 21 degrees Celsius as converted into ice at negative 11 degrees Celsius. So we are starting with a liquid water, and then it converts, we have our heat of fusion, and then we have our solid, our ice. So when does water become ice? At what temperature? 0. All right. And we're just having water at 21 degrees Celsius, so that can be anywhere on that slope. And then we are going to our other slope, and we're taking it less than 0 to negative 11. So we have 3 things. We have a slope, a straight flat line, and another slope that we're working with. So that means we have to do 3 different steps to figure this out, how much energy is being used. So we're just going to go working backwards from our liquid. So our liquid, we use Q equals MCAT. The mass of our water is 25. The C of liquid water is 4.18. And our change in temperature is from final is 0 minus 21. So to 2 sig figs. Yes.
don't you remember we have to do 2 of them? If you do like the ice and water one, then 2 is 0. So So you don't do Q equals MCAT for that one?
I had to do Q equals MCAT for each slope,
Just the slopes.
for the slopes. And then for the straight line, I have to do heat of fusion. Q equals H. 2200, negative 2200? Okay. And then now let's go to our straight line. So Q equals, the mass is still 25. And then if you go to our graph, or our page before, what is the heat of fusion for water? Is it 335? I think it's 335. 335. So when you solve for that to 2 sig figs, I get 8,400 joules. Okay, so now Q is just going to give us a quantity, and we just need, for this, and we have to figure out what's the sign going to be. So our sign is going to be the same that it was for MCAT. So since MCAT gave us a negative sign, then our heat of fusion, it has to be a negative sign. And then we go and we do Q again for the solid, for the ice. So Q equals MC delta T. Our mass is still 25, but what is the C of water when it is ice? 2.03. And our delta T is going from 0 to negative 11. Or negative 11 to 0. Whoa, final minus initial. Whoop. And what do you guys get for that? 560, negative 560. And your last step is to see what the Q total is. So how much energy total? So we have negative 2200 plus negative 8400 plus negative 560, negative 11,000 joules to 2 sig figs. Okay, any questions on that? Okay. So we're going to talk about phase diagrams real quick, and then we're going to get into the meat of our lecture for today. So this is called a phase diagram. You see that it has all of our phases on there. Some call it the butt cheek diagram because here you have here you have the crack of the butt, and then you have the cheek and the cheek. So they call them butt cheek diagrams. And one cheek, on your left cheek, it's a solid. Your right cheek is a liquid. And then out here from the butt is your gas. Okay. So this is a butt diagram. You have, what it's doing is it's comparing pressure to temperature. What happens to your solution or whatever you have as you increase the pressure or you increase the temperature. So on the line is your equilibrium point. Okay. And then over here is your critical point. So anything past your critical point is going to be gaseous. And then I want you to notice that you have this positive slope. The butt crack is a positive slope. So if you have a solid and you increase the pressure, what happens? Do you change phase? You still stay a solid, right? Okay, so this is anything but water. Water has a different phase change diagram. And water looks like this. So its butt crack is a negative slope. So what happens if we have pressure and temperature? So if you're ice skating and you get onto the ice and you have a lot of pressure, as you start ice skating, that solid ice becomes what as you increase your pressure? Becomes liquid. So will you ice skate on liquid? Okay? So when you're ice skating, that is on liquid. When you get onto the ice with your shoes, that is, you're on ice. But because the blade of the ice skate, it has so much pressure on that solid, it converts it to liquid, and that's what causes it to you to ice skate. And then once you push off of it, it turns back to ice.
How does it do that?
That's the funny thing about water, because of the hydrogen bonds, and it's how it is.
So does that mean anything with hydrogen bonds is?
Not any, I would say because of water's uniqueness, how water is. Yes. So there you go. You're not really ice skating, you're water skating. Okay, so any questions on phase diagrams? Oh, does she, will you hand her the pass?
Is that why, like, the center of the Earth, they think it's solid metal? Even though it's really hot?
There's so much pressure it can't be.
And the temperature, I don't know. Don't ask me anything about that. All right, so here we go. London, we're going to talk about these actual forces now. So London dispersion forces, those are the easiest ones. What happens is you have to have this instantaneous dipole, and it occurs. And when it hits a neighboring atom, you will get that instantaneous dipole. So you might have an atom that looks like this normally, but once it hits something else, it may look something like that. So you get this instantaneous dipole. So now here you have your partial positive, and then here you have your partial negative. So what happens is we have an electron cloud shift. And that's what causes us to have that instantaneous dipole. When you have very large atoms or very large molecules, this is very significant because they have lots of electrons. Okay, so because we have lots of electrons, LDFs are going to be significant in these atoms. Now, all molecules, whether it has polar or hydrogen bond or dipole or hydrogen bonds or whatever, they all have London dispersion forces. They all have them. Just because it's dipole, you don't have to put LDF there. LDF is occurring, but it's not a priority. It's the dipole would be the priority. So you do need to know that these occur in non-polar molecules. So all non-polar molecules have London dispersion forces. So what we say about these, we say that these atoms are polarizable, which means their big or their large electron cloud causes it to have strong intermolecular forces. So when you have a nonpolar molecule, only thing you're going to have, the intermolecular force, is London dispersion. So if you will take a look at my periodic table, you have chlorine, bromine, and iodine. Chlorine is in red, which means what is its state of matter at room temperature? Gas. Bromine is blue, so it means it is liquid. Iodine is solid. So,
What about the ones that like don't have anything in
those are man-made.
The coal.
So, if you will look at that, why is at room temperature iodine a solid, whereas chlorine is a gas? They're all nonpolar molecules, right? So they all have what type of force going on in them? London dispersion. But why is one a gas, one a liquid, and one a solid? They all have the same intermolecular force. What is making them different? Which one's larger?
Iodine.
Iodine. So iodine has more electrons, which means it is more polarizable, which means it has a stronger IMF. Stronger IMFs mean that it's going to be held together. Those molecules are going to be held together and make it a solid. Whereas if you have a weaker IMF, you're going to start to become a gas.
So it does have a stronger IMF
It's a stronger IMF because
because of its
of the
size.
size, because it's more polarizable, because it has a large electron cloud.
So why is shielding? Why is Mercury? Right? H3. Why is Mercury?
Dude, it always is shielding.
I mean, it has. Sorry, just questions.
Okay, any questions on LDFs? All right, next. Dipole, dipole. So these are when we have polar bonds. And so if we have, say, HF, and we have our polar bond, then we have a dipole moment. Now, if we have another HF around here, then we have a dipole moment here, and this is where you get that dipole-dipole interaction. Okay? So dipole-dipole is in nonpolar bonds. A hydrogen bond is in a polar molecule. Dipole-dipole is in a polar molecule. Now, polar molecules, of course, do have the LDFs, but we are more focused on the polar, or the dipole-dipole. Questions? And then lastly, hydrogen bonding. It's not really bonding. It's really an electrostatic force holding these things together. But we call it bonding. And these occur between hydrogen and either nitrogen, oxygen, or fluorine. This is stronger than a regular dipole-dipole bond. Marcus just looked at her.
Maybe just.
Okay.
Louis, speed him up.
I'll let my mom. And they were just like, you have to tell your mom so that when you come home, she doesn't like call us.
You'll see bruises all over you. Okay. So the next couple of slides are for your information only to go back. And you'll have a POGL tomorrow. and it'll go over some of these. What you see here is our melting and boiling points, and you see that the higher your melting point and your boiling points, then the stronger the intermolecular forces. So you need to know that if you have a high melting point, then you have a strong intermolecular force. Again, because it's taking a lot of energy to go from solid to a liquid. If you have a high boiling point, again, you have a strong intermolecular force that needs to be overcome so that you can go from a liquid to a gas.
Is it possible to have a low melting point, high boiling point?
I don't know. I don't think so. Okay, so take a look here. CH4. We all agree CH4 looks like this. Right? What type of molecule is it? Polar, nonpolar? It is a nonpolar molecule. And then if you go up here to water, and water looks like this, what type of molecule is water? Polar. And so we can see that water has a high boiling point as opposed to CH4 because the polar molecules being held together by, or the polar molecules are being held together by what type of force? Water is held with hydrogen bonds, while CH4 is being held together with London dispersion forces. Questions? Okay. Which molecule is capable of forming stronger intermolecular forces? So if we have nitrogen, my suggestion is I would draw these out, the Lewis structures out, so that you can see what's going on. So which one is the stronger intermolecular force? Oh, that was supposed to be NN. Jeez. So NN, what is the IMF in NN? LDF, because it is nonpolar. And in water, it is polar. And what's holding those molecules together are hydrogen bonds. So our strongest one is water. So now I'm going to draw two structures of C2H6O, and we're going to compare the boiling points of those two molecules. So these both have the same formula, so they are carbon-carbon. And we have 7 molecules that we have to put around it. So we have hydrogen, 1, 2, 3, 4, 5. And I need 2 more molecules, but I only have 1 spot to put it. So we're going to add a hydroxide here. So what type of molecule is this? Polar, nonpolar? Polar. Where is the dipole moment? Goes that way. Okay. This is anybody know what OH, what type of group that is? Organic group, if you end in OH?
Alcohol.
Alcohol. Okay, so this is an alcohol. And alcohols at room temperature are liquid. Okay. Now we're going to draw something different here. We're going to draw, rather than carbon being the central, we're going to put oxygen in the central. So we call this type of group that looks like this is not an alcohol, this is called an ether. So what type of molecule do we have going on here?
It looks
Nonpolars. Our dipole moments are going that way, so we don't have an overall dipole moment, so it is nonpolar. Anybody know what ether is at room temperature? It's a vapor, so it's a gas. So we have what type of force going on in here is LDF. So who's going to have the higher boiling point? The alcohol, right? It's not going to take much to take that ether and turn it into a gas, okay? Questions on that? So you need to be able to compare those, look at those, see what's going on. Smelling salts? So here says which one is going to behave more ideally at the same conditions. So if I were to draw this and I have carbon monoxide and I have nitrogen, I want to know which one's going to be more ideally if it's in it as a gas. So the first thing you need to remember that as a gas, to be an ideal gas, you have to have, those molecules have to have low attraction to each other, and they have to be small to be an ideal gas. So if we look at these, they look like they're probably about the same size. Let's look at the polarity. CO, what is its polarity? It's polar. NN is nonpolar. So what kind of force of attraction do you have in CO? Dipole. And in nitrogen you have LDF. So which one's going to act more ideal? Which one's going to have the low attraction for each other? Nitrogen. We're going to go through the next slide really quick, and then we're done. All right, so tell me, what IMF is going on in all of these? So CH3OH, that is an alcohol. So what intermolecular force is being played in that one? What's its polarity? It's polar. So what's going to be hydrogen bond or dipole? Hydrogen bond. Any alcohol will be a hydrogen bond. Xenon. A xenon, so this would be a single atom, so it's going to be nonpolar since it's with itself. It's very huge. So what would its intermolecular force be? LDF. H2S, what's its polarity? Polar. So what is its intermolecular force? Dipole? CLF, what's its polarity? Polar, and its force? Dipole. And lastly, calcium nitrate. What's going on here? That is a salt. Good. So what type of bond is it? What is it? What's the bond between it? Ionic. And any ionic bond is being held together by what? It's not an intermolecular force. It is being lattice energy.
Me too,
Okay. So your homework tonight is 11A, and then tomorrow you will have the POGL.